Here are examples of four objects moving along vertical circular paths. We have a ball on a string being swung in a vertical circle like this, or a car going over the top of a round hill. As it's going over the top, it's moving along this top portion of a circular arc. That's circular motion. Or say at the bottom of a round valley here. Moving along the bottom, you're going along the bottom of a circular arc through that dip right there. Or this pendulum here swinging back and forth. Even if it's not completing the full circle, it's going along this bottom portion of a circular arc. That is vertical circular motion as well. So I want to examine the dynamics of this kind of motion, and we'll focus on our ball scenario here. So a ball being swung on a string. Okay, I've marked off 3 points when the ball is at the bottom, at the side, and at the top as it swings around counterclockwise in this circle on the string. So we see there are two forces, tension and force of gravity, and we ought to begin with our free body diagrams and then check out our axes and then set up Newton's second law. Some additional information I've put on here would include the velocity vector at each of these 3 moments. So let me draw your attention to the blue vector at those 3 moments, the velocity at point A, point B, and point C. And we're reminded that your velocity is always tangent to your path at all points along your path. So it's always tangent to this circle. And of course, the ball will slow down under the influence of gravity as it heads toward the top and then speed up on its way back down. Hence we see our velocity arrow being largest here, smaller there, and then smallest at the top, but not 0 at the top. Okay, now our actual free body diagrams. I've got those vectors drawn in red. So at the bottom, tension and gravity. And before we go any further, let's discuss the most common mistake that students tend to make when considering vertical circular motion. It happens here at the bottom, the lowest point. Our most common mistake is to assume at the bottom that the upward force of tension and the downward force of gravity are balanced, to assume that these two are equal at the bottom. That is incorrect. That cannot be the case. And let's take a moment to consider why. If they were equal, here's the thought process you can walk yourself through. If these two forces were equal at the bottom, then the net force would be 0. And if the net force on an object is 0, then its acceleration is 0. So when your acceleration is 0, you continue to move in a straight line with a constant velocity. So if those two forces were equal, it implies that the ball would just continue to move off to the right in a straight line. It would not curve upwards along its path. Therefore, we conclude that tension has to actually be greater than the force of gravity at the bottom. They cannot be equal. Tension must be greater than gravity, so we have a net force upwards, or more to the point, a net force in towards the center of the circle, a centripetal net force, so that with our velocity to the right and our net force pulling upwards toward the center of the circle and acceleration upwards, let's let this red pen be the acceleration, with velocity to the right and acceleration up, the acceleration is going to be pulling the velocity vector upwards. This tension here overpowering gravity is going to be tilting velocity upwards, pulling upwards on that, curving the path of the object so that it does not continue to go straight. Okay, so that was probably the single most important thing to cover. Let's get back to our dynamics at that point and at the other points. Okay, so we've got our FBDs. Gravity, we see the force of gravity is the same at all 3 points, and our tension ought to get weaker as we head towards the top. It might go to 0 at the very top, but not necessarily. So tension getting weaker. And I've indicated tension A, tension B, tension C to remind ourselves that the tension does not stay constant in magnitude. That will vary just as our velocity, VA, VB, VC, varies in magnitude as well. Okay, those are FBDs. Now, as for our axes, if we're moving in a circular path, we know we need a centripetal acceleration at all moments. At least some component of our acceleration needs to be inwards toward the center of the circle in the negative radial direction. So we want to choose axes that align with that. So we want a radial axis pointing outwards at all points and a tangential axis pointing in the direction of motion. We choose counterclockwise here, so tangent and counterclockwise. So here are our r hat and t hat unit vectors at all 3 points. And notice again how they rotate along with the object. So at the bottom, if my thumb is r hat and my index finger is t hat, r hat and t hat at the bottom rotate to point B over here and then rotate again to point C at the top. Okay, so there's our rotating r hat and t hat radial and tangential axes. And now we're ready to set up Newton's second law. I'll do it for point C at the top first. What you should always do is state N to L in its general form here, and we'll have one statement for each of our directions, once for the radial direction, once for the tangential direction. So AR equals net force in the radial direction over mass. State that first, and then express your sum of forces. So here at the top, we have gravity in the negative radial direction, and tension also in the negative radial direction, both centripetal, both pointing towards the center, hence the minus FTC and minus mg over the mass. And then here's the key new thing to add to Newton's second law. We're going to set our radial acceleration equal to minus v squared over r. Let's go back to a reminder on our circular kinematics here. Our radial acceleration, if we're moving along a circular path, can always be set equal to either minus omega squared r, our angular speed, or minus v squared over r, v, our linear speed. Also, the tangential acceleration can always be set equal to alpha, the angular acceleration, times r, if we're on a circular path. So we're going to set AR equal to this and AT equal to this every time we set up N to L for those two directions. So AR equals minus VC squared over R. And then if we're trying to solve for something, most of the time we would focus on this equality here and we'd be trying to solve this equality for whatever quantity we wanted to know. Now in the tangential direction at the top, no forces tangentially to the left or right. So 0 is our angular acceleration, alpha c, and our tangential acceleration at the top. Okay, let's go to point B. B at the side here, once again, state radial acceleration equals net force in the radial direction over the mass. Then check for our radial forces here. We have only tension pointing in the negative radial direction in toward the center. So minus FTB over M, and set that equal to minus V squared over R. And then this typically becomes the equation that you're working with as you try to proceed to solve for something of interest. In the tangential direction, net force in the tangential direction over the mass, let's see, here we actually do have a tangential force. It's gravity pointing opposite our t hat vector. So gravity is pointing in the negative t hat direction, hence minus mg for our force of gravity. We notice that mass will happen to cancel out in this case, and you set that equal to alpha r. Tangential acceleration gets set equal to alpha r. Okay, and lastly, point A here at the bottom. One more time, set up our radial acceleration. This is our centripetal acceleration equals net force in the radial direction over the mass. And here's our sum. Looking here, we have tension upwards, but upwards is toward the center, and our r hat vector points straight down because radially outwards is down at this point. So this tension is actually in our negative radial direction, that's centripetal, so minus Ft. It's your job to put that minus right there. Whereas our force of gravity, it's down, but that's in our positive radial direction, r hat direction, so plus mg right there. And set that equal to minus v squared over r. And end up solving this equation for whatever it is that you want to know. No forces in our tangential direction, So 0 tangential acceleration, 0 angular acceleration at point A. Okay. The last thing that I'd like to do on this diagram is consider our acceleration vectors. We've got the force vectors, the velocity vectors, but what about our acceleration? Well, at each point, we know that the acceleration will be in the direction of the net force. That's what N2L is telling us here. So at the bottom, FTA is greater than FG, so our net force is upwards towards the center. So our acceleration will also be upwards towards the center. Let's say like that for our acceleration vector there, in the direction of the net force. At the top, our acceleration is in the direction of the net force, so gravity's down and tension's down, so they're adding up. So we're going to get a large net force downwards, and that'll give us a large acceleration downwards as well. So there's our acceleration vector at the top. And at the side here, our net force can be found by using the parallelogram method for adding vectors, since we've already got them tail to tail in this FBD. So we would make those two forces the two sides of a parallelogram and draw in the diagonal of that parallelogram. That diagonal would be the direction of our net force, so that diagonal is also the direction of our acceleration. So note how at the bottom our acceleration points straight up, but then our acceleration vector, as we swing upwards, must sort of tilt. So acceleration points like that by the time we're at the side, and then tilts some more until it points straight down at the top, and then we'll reverse that trend on the other side.